All right. Hi, everyone. My name is John Donahue from the Institute for Quantum Computing, here to give you today a quick introduction to quantum computing. So this is for the ECE 405 class. So we're going to kind of break this down into three chunks. First, we're going to talk about quantum bits. So you hopefully already heard a little bit about the Stern-Gerlach experiment. We're going to be talking about other kinds of systems we can make quantum bits out of, and how we think about a quantum bit of information, how we encode a bit of information into a quantum system. In the next session, we're going to be talking about quantum gates, how we manipulate these quantum systems, and then finally, we're going to go into quantum algorithms. So we're going to be talking about a fairly useless problem, but we're going to learn some of the lessons of how we solve algorithms using quantum bits to hopefully help us understand more useful algorithms later on. So the first bit on quantum bits, if you're really, really clear on the Stern-Gerlach experiment, we're not going to be talking too much about it, but you might be able to skip that. For the quantum algorithm session at the end, we're going to be getting into the weeds a fair bit with the mathematics, but I'm really hopeful that in this kind of middle section, that's where, we're able to pick up something. So this is going to be a theoretically minded lecture. We're not going to be talking too much about like really specific experimental things. In the description on this YouTube channel, you should be able to see a link to a Google Drive with both the slides and the notes for the third section. We get some really detailed notes on those quantum algorithms at angles. So first off, we want to talk a little bit about quantum bits. So a quantum bit of information is any kind of quantum system where we can encode one binary bit of information. So hopefully you already heard a little bit about spin, about Stern-Gerlach. We'll come back to that, but I actually want to start by focusing on something that is sometimes easier to think about, easier to see with your eyes. And that is the polarization of a single photon. So we know that light is an electromagnetic wave. Light carries an electric field. If I'm a beam of light and I'm traveling towards you, I am carrying an electric field with me, and that electric field is going either up and down like this or side to side like this, some direction perpendicular to the direction of the beam's travel. The direction of that electric field is called the polarization. Now then, there are two what we call mutually exclusive states of polarization. If the photon is horizontally polarized, it is definitely not vertically polarized. If it is vertically polarized, it is definitely not horizontally polarized. We can see this using good old-fashioned polarizing filters like the one I have in my hand here that unfortunately are very clear when you use them in person and very difficult to pick up on a camera. We're going to try our best right now though. So these polarizing filters all have a little line on them. So this line indicates that if the beam of light is polarized in that direction, so in this case horizontally polarized, it passes straight through. If it's polarized in the opposite direction, it gets absorbed. So any vertically polarized light gets absorbed here. If I hold this polarizing filter up here, you can still see my face through it. All the light that's traveling from my face to the camera, all that light is horizontally polarized. This filters out all the vertical polarization. If I hold another polarizer like this, it filters out all the horizontal polarization. I'm only left with vertical. You can still see my face through either one because light is fairly unpolarized in this room. But if I put the two of them together, then that really blocks out almost all of the light, just a little bit of experimental imperfection there. So we see that if we block out the vertical light, so we only have horizontal light, and then I ask the question, are you vertical? It says no. If it is horizontal, it is definitely not vertically polarized. So this is the concept of a mutually exclusive state, which is going to be very, very important here. Two states are mutually exclusive if they are distinguishable and impossible to confuse. So if it's impossible for a perfect machine to mix them up, and if they cannot both occur at the same time. This is not a quantum concept. For example, a coin has two mutually exclusive states. It is either heads or tails. It cannot be both heads and tails, and assuming that it's, a nice polished coin, that it's not, completely covered in muck or something, I can very perfectly distinguish whether or not it is heads or tails. A light switch can be either up or down. We're not talking about dimmer switches here. The light switch is either up or down, one of two possible states. For one that's often brought up in terms of quantum context, the cat is either alive or dead. It is not both alive and dead. It is one or the other, and hopefully it's easy to tell which one it is. And if we want to abstract it away, we can really think about this in terms of binaries, zeros and ones, some electronic signal, some spin state in a memory drive or something like that. It is either in the zero state or the one state, and we can hopefully measure and determine which one it is. In the quantum case, there are a ton of examples. We're going to talk about some of them near the end of this, and you'll learn a lot more about those when talking about implementations. But two examples that you've already seen are electron spin. The electron can either be spin up or spin down. It can only take one of these two distinguishable values. The photon polarization can be horizontal or vertical. To emphasize with the photon, we're really talking about one single particle of light carrying that polarization value. It is straightforward to encode binary information in any of these systems. I can, build a computer basically that encodes zeros and ones in is the coin heads or tails? Is the light switch up or down? Is the photon horizontal or vertical polarization? Think about it this way. I can send you a string of zeros and ones by sending you light pulses, and the zero is encoded as the light pulse being horizontal, the one is encoded as the light pulse being vertical. So I can easily encode binary information into the polarization of light or any of these other systems. It is probably inhumane to encode binary information into whether a cat is alive or dead, but theoretically speaking, you can do it. All right, so let's look at this polarizer again, but really keeping our heads on thinking about we're dealing with one photon of light, one indivisible particle of light. So a photon is, it's the particle nature of light there, but it still carries electromagnetic energy. It is still the carrier of the electromagnetic field. So that photon, its electric field, still has a polarization. So if I have my single photon and I hold up a polarizer and I ask my photon to pass through the polarizer, there are two possibilities. A, the photon passes through this polarizer, which analyzes its polarization, or B, the photon is absorbed by the polarizer. When we think about bright beams of light, we think about the intensity that is absorbed versus the intensity that is transmitted. When we're thinking about one single photon of light, we must consider the probability of each event occurring. So what the polarizer is doing is it is asking the photon a question. If I hold my polarizer like this, it's asking the photon the question, are you horizontally or vertically polarized? If horizontal, get absorbed. If vertical, pass on through. But is this the only question that I can ask my photon? Well, no, because I can hold my polarizer like this, or any angle in between. Okay, so I could also ask it the question, are you diagonally or anti-diagonally polarized? So anti-diagonal being just the negative diagonal. So if I have my diagonal polarizer here and I bring in a negative diagonal polarizer, same as we saw with horizontal and vertical, that blocks out basically all of the light. So I can ask the photon this question, and if it's diagonally polarized, it's going to pass through. If it's on the negative diagonal, it's going to be absorbed. Okay? So, if my photon was horizontally polarized and I asked it the question, are you horizontal or vertical? It would tell me, well, I'm horizontal. But what happens if I ask it the wrong question? Like, for example, what happens if I have a diagonally polarized photon and I ask the question, are you horizontal or vertical? How can it answer that question? So let's break that down a bit. So we're going to start off with a diagonally polarized photon. So we've started off with a source of photons, a diagonal polarizing filter. So everything that makes it through that diagonally polarized filter is now diagonally polarized. I now have one single diagonally polarized photon, and I ask it the question, are you horizontal or vertical, using a vertically polarizing filter? To answer this question, I have to think about, okay, I have my diagonally polarized photon. How can I describe it in terms of its horizontal and vertical components? Okay? So the way I'm going to do that, I'm going to look at basically a Cartesian coordinate system. I'm going to look at my diagonally polarized photon. It has an electric field in this direction. I break that down into having a horizontal component of 1 over root 2, just using good old-fashioned cosine sine laws, and a vertical component of also 1 over root 2. It has an equal component horizontal and vertical. So I could think about, how do I make a diagonal line using only horizontal and vertical lines? I do that using one horizontal and one vertical line. Now then, in terms of how this connects to probabilities, well, this single photon has a 50% horizontal component and a 50% vertical component. The interpretation there is that there is a 50% probability that the photon is transmitted and a 50% probability that the photon is absorbed. I actually have these two backwards in the slide. It should be transmitted for the vertical, absorbed for the horizontal. Sorry about that. If it transmits, it is now definitely vertically polarized. We've put it through that vertical polarizing filter. We've removed the horizontal component. So if we see that photon pass through that vertically polarized filter, it is now definitely vertically polarized. Okay, so there's a bit of a conundrum that happens when we start introducing more and more polarizers. So we already saw this situation. We had our plus 45-degree polarizer here, our minus 45-degree polarizer here. If we sent in a beam of light or a stream of single photons, anything that makes it through the plus 45-degree polarizer is now definitely positive 45-degree polarized. And when it encounters that negative 45-degree polarizer, it definitely gets absorbed because negative 45-degree polarizers only let through negative 45-degree polarized light. What happens if we insert another polarizer here at 90 degrees? So something straight up like this. What's going to happen? So once again, it doesn't really come up on the camera, but if you happen to have a few polarizing filters at home, if you happen to have a big string of sunglasses, you can test it out yourself. So let's analyze it step by step by step. We start off with a diagonally polarized photon, and that diagonally polarized photon is going to encounter next, so this is our diagonally polarized photon here, it next encounters a vertical polarizer. Okay, so we're asking the diagonally polarized photon the question, are you horizontal or vertical? In order to answer that question, we have to break it down in the basis of the question being asked. So we have to break down our diagonally polarized photon into horizontal and vertical components. Okay, we do that using a Cartesian circle. We can also do that by just thinking about how we build up a diagonal arrow out of horizontal and vertical arrows. And just as before, we find that there's a 50% probability that the photon is absorbed, a 50% probability that the photon is transmitted because it is a 50-50 superposition of horizontal and vertical components. So with a 50% probability, the photon makes it through. We can tell that based on the components. And if it transmits now, it is definitely vertically polarized. Okay? So with a 50% probability, we end up with a vertically polarized photon right here. Now we have our vertically polarized photon, and we ask it the question, are you diagonal or anti-diagonal? Are you plus or minus 45 degrees? Once again, the vertical polarized photon is like, well, I'm not minus 45 degrees, but I'm also not minus 45 degrees. I'm, somewhere else. I'm not negative 45 degrees. I'm also not positive 45 degrees. We're asking the photon the question, are you plus or minus 45 degrees? For it to answer that question, we need to break it down into its plus and minus 45 degree components. Okay, so same as we did for the diagonal light where we broke it down into horizontal and vertical components, we're basically going to look at the projections of this vertical light onto a plus and minus 45 degree Cartesian axis. So if you're more comfortable with it, just as we thought about breaking down the diagonal polarization into a horizontal line and a vertical line, we can think about breaking down the vertical polarization into a plus 45 degree line and a plus 135 degree line. Okay, and by doing that, we can see that, okay, that vertical polarization is, just as diagonal polarization was a superposition of horizontal and vertical components, vertical polarization can be thought of as a superposition of a diagonal component and an anti-diagonal component. Because we need to kind of flip this arrow upside down to make it work, we put a minus sign here. That's going to be important later. For now, we're still just building up arrows. The important thing is that it's a 50-50 superposition. So when the vertical photon encounters the diagonal polarizer, with a 50% probability, it's absorbed. That's this component here. With a 50% probability, according to this component here, it passes through. Transmits again with a 50% probability. So overall, if I get rid of this polarizer in the middle, there's a 0% probability that a photon makes it from here all the way to here. But by inserting more measurements in incompatible bases, like by inserting more measurements that are not compatible with each other, all of a sudden we end up with a 25% probability that this photon makes it through. As a challenge problem, if you want to get through the math, see what happens as you add more and more polarizers here. You're going to find that eventually, in the limit of infinite polarizers, you can actually have two perpendicular polarizers, an infinite number of slightly twisted polarizers in the middle, and eventually end up with a 100% probability of a photon making it from here all the way to the end, just through measurement alone. So what does this mean? Let's kind of think about this through what we sometimes call the two golden rules of quantum mechanics. And those are the rules of superposition and measurement. So we have our diagonal and our negative diagonal states. We're going to surround them in kets, just to emphasize that we're talking about a single photon and its polarization state. Okay, so this diagonal is a superposition of a horizontal and a vertical component. This antidiagonal is a superposition of a horizontal and vertical component. We just flip that vertical component upside down. So is the photon, if it's in this diagonal state, is it horizontal or vertical? Well, it's got a component of each. So in a way, it's horizontal and vertical at the same time. But if I ask it the question, are you horizontal or vertical? It's going to be one of the two randomly. Okay. So before measurement, it's both at the same time, a little in a way, in a sort of way. It's in a superposition of both. It has a component of each. But when I ask it the question, are you one or the other? It's not going to tell me both. It's going to tell me I am horizontal or I am vertical randomly. But this works both ways. I can invert this just as well. So if I have a horizontally polarized photon, it can also be thought of as a superposition of diagonal and antidiagonal. Same with vertical. In this sense, the horizontal photon is both diagonal and antidiagonal at the same time. But when I measure it in the diagonal-antidiagonal basis, it's going to be found as one or the other randomly. I'm using the word basis a lot here, which is a term that we borrow from linear algebra, and it's an important one. It defines which question I ask the particle. And we see right here, and based on how we play with these polarizers, there are incompatible types of questions, incompatible bases. I can learn whether or not the photon is horizontal or vertical, but learning whether it is horizontal or vertical disturbs that information about whether it was diagonal or antidiagonal. As we saw when we inserted this extra measurement here, it disturbed the overall system because it was in a different basis. Okay, and we can also see this mathematically. So if you're having some trouble seeing how we think about like a horizontal photon as a superposition of diagonal and antidiagonal states, we'll just kind of expand these out. We can always, look at the expansion of diagonal as this state in the horizontal vertical basis, antidiagonal in this basis, and we can really cleanly see that the vertical components cancel out and that diagonal plus antidiagonal gives us a horizontally polarized photon. Okay, so let's connect this back to the Stern-Gerlach experiment. So remember the Stern-Gerlach experiment. They had this oven. It came out with randomly spinning electrons. They put it through an inhomogeneous magnetic field aligned in the z direction. They expected that if you were to have a random spin orientation, you should see a random blur of possible say this is like some kind of electroluminescent screen, something that glows or turns color whenever it sees an electron. You would expect to see, a random smear here. What they instead found was that 50% of the electrons ended up at this point, 50% of the electrons ended up at this point. Okay. For the record, all of these figures on the Stern-Gerlach experiment are credited to Richard Epp. Okay, so this had no classical explanation at the start. What they did find, though, was that if they took the 50% of those that did go to the upward path and then put them through a second inhomogeneous magnetic field, 100% of them went upward. So if they went upward the first time, they would always go upward the second time. Similarly, if they went downward the first time, they would always go downward the second time. So if they took their separated electrons, passed them through another magnetic field, the results were no longer random. The conclusion they had is that, well, the electron spin has two mutually exclusive states. Just like we had horizontal and vertical polarization as our two mutually exclusive states, anything that all the electron spins are one of two possible states, either spin up or spin down. After they come out of this magnet, the top path are all spin up, the bottom path are all spin down, and if we do further measurements on them, we find that yes, they were all spin up or they were all spin down. So in a third experiment they did, they kind of twisted one of the magnets by 90 degrees along a different axis in the x direction. And they found the exact same split. Okay, so now we're no longer talking about spin up and spin down, which all comes from the right-hand rule. We're kind of twisting our head this way and thinking about like spin left and spin right. And once again, it splits up 50% spin left, 50% spin right. But what happens then if they take this spin left electron and put it through a Z magnet? They once again see that 50-50 splitting. Okay? So even though we had a definite spin here, if I put another X magnet, it would definitely go left again. If I put a Z magnet here, I get a random distribution again. Same if I put the Z magnet on the spin right side. This should be pretty familiar from our polarization example as well. We're seeing very similar effects. If I ask a horizontally polarized photon, are you diagonal or anti-diagonal? It had a definite polarization before, but because I've asked it an incompatible question, it is one or the other randomly. Way to think about that in terms of the spin states is that spin left and spin right are superpositions of spin up and spin down, which we can think about as, same as we thought about with polarization, a component spin up and a component spin down gives us a spin right. We're calling spin up and spin down 0 and 1, spin left and spin right plus and minus. Right. In a final experiment, or the final of the traditional Stern-Gerlach triptych, we start off with our spin up polarized electrons, and then if we had inserted another Z magnet here right away, we would have found that they are all still spin up. But if we insert an X magnet in the middle, and then only look at the ones that go down one path of the X magnet, we find that if we insert a Z magnetic field again later on, all the electrons then are randomly mixed up again. We see some spin down components. Okay? So it started off spin up. We asked the spin up electron, are you spin left or spin right? And then we asked the result of that, are you spin up or spin down? And even though we originally know that they were spin up, we do see some spin down component. Okay, and the way to imagine this is that it's reversible. Those Z spins can also be thought of superpositions of X spins. Or another way to think about it is that the measurement that we make here, when we make this X measurement, it disturbs the state. So this spin up state was a superposition of spin left and spin right. When we isolate that spin right component, that we have to think about that spin right component as a superposition of spin up and spin down. So we can see some spin down probability coming out at the end here. So these two experiments, this 3-polarizer experiment and this 3-magnet experiment, look very different. If I want to build them in the lab, I need a very different set of tools. But if I'm a theoretical physicist, if I'm a quantum information scientist, these are the same thing. The exact same thing. We're dealing with a two-level system that has two mutually exclusive states, spin up, spin down, horizontal or vertical polarization. And when we insert an incompatible measurement in the middle in both scenarios, it disturbs the system and we see components that we shouldn't have normally seen before. The spin up seems like it actually has a spin down component. The diagonal polarization seems like it has a negative diagonal component, and those components arise because we ask these incompatible questions in the middle. All right, for the rest of this kind of talk, we're not going to really be thinking about anything physical anymore. We're going to be thinking about these in the abstract. We're going to be thinking about states as vectors, really. So quantum states are described by unit vectors in complex, potentially high-dimensional Hilbert spaces. Don't worry too much about what Hilbert space is, the complexity of it for the moment. The important thing I want to talk about right now is this unit vectors. So let's consider that electron spin again. It can take one of two possible values, spin up or spin down. We're going to represent them as a pair of orthogonal unit vectors. So spin up is going to be the vector 1, 0, the x unit vector. Spin down is going to be the vector 0, 1, the y unit vector. We want them to be unit vectors because we're dealing with one single electron. And as we'll see that when we're using these to calculate probabilities, making sure they're unit vectors will make sure that our probabilities all sum to 1. And why orthogonal? We want to emphasize that they're impossible to confuse. A spin up electron has no spin down component. A horizontally polarized photon has no vertically polarized component, just like an x vector movement along the x direction has no y component. We're going to surround these in kets just to look fancy for now, but we're going to actually see that they're very useful at the end of the day. So the 0 ket, we're going to just assign it a binary label 0. That's that x unit vector 1, 0. And the 1 ket is going to be the y unit vector 0, 1. We call any two-dimensional quantum state a qubit. A qubit is a quantum bit. We can use this to encode binary quantum information. So our two golden rules, but now in the form of kind of abstract quantum bits. The plus state is 0 plus 1. The minus state is 0 minus 1. The particle is both in the state 0 and the state 1 at the same time. It is both encoding the bit 0 and the bit 1 at the same time. It has a component that is 0 and a component that is 1. But when I measure it in the 0, 1 basis, when I ask it the question, are you 0 or are you 1, I find 0 or 1 randomly. Similarly, I could think about 0 as being a superposition of the plus state and the minus state. I can think about 1 as being a superposition of the plus state and the minus state with a different phase in the middle here. The particle is in both the plus and minus state at the same time, but when I measure it in the plus-minus basis, I'm going to find it to be plus or minus completely randomly. So once again, really want to emphasize that the measurement basis defines which question I ask the particle. And we talked about two systems, but this is applicable to a ton of systems. Any system where I have one of two possible levels, when I have two mutually exclusive states, they follow the same rules. Spin does, photon polarization does. If I have a two-path interferometer and I insert one single photon, it's going to follow the same rules. If I have an electron and I restrict it to only occupy one of two possible energy states, it's going to follow the exact same rules. They all require very different tools to work with as an experimental physicist or engineer, but to a theoretical physicist, to a mathematician, these are all the same. So in the next part, we're going to be talking a bit about quantum gates. Go grab a coffee, and I'll see you on the other side.